Hello! Welcome to today's lesson on the magnetic field produced by a current-carrying wire. We will begin today's lesson by exploring how a magnetic field is produced around a conducting wire when an electric current flows through it. Next, we'll examine the concentric circles that form the magnetic field around the wire, and how the direction of the current influences the field's direction. Finally, you'll learn the right-hand grip rule, a useful method to determine the direction of the magnetic field around a current-carrying wire. So far, you are familiar with the fundamental characteristics of magnets, the concept of magnetic field lines, and how to draw these field lines. Building on this foundation, we can now understand how electric currents generate magnetic fields. Let's get started. When an electric current flows through a conducting wire, it generates a magnetic field around the wire. This phenomenon can be demonstrated using a simple setup involving a straight conducting wire, such as a copper wire, and a compass needle. First, place the compass needle near the straight conducting wire and note the initial direction in which the compass needle points. Then pass a current through the wire. You will observe that the compass needle gets deflected. The deflection of the compass needle demonstrates the presence of a magnetic field around the current-carrying wire. The magnetic field created around a current-carrying wire has some specific characteristics. Specifically, you'll notice it forms concentric circles that are centered on the wire. This means if you were to look at a cross-section of the wire, you would see rings of magnetic field lines encircling the wire. Additionally, the direction of the magnetic field depends on the direction of the current flow through the wire. A crucial difference between this magnetic field and the one around a bar magnet is that the magnetic field around a current-carrying wire does not have north and south poles. Let's now turn to the strength of this magnetic field. This is influenced by two main factors, the magnitude of the current and the distance from the wire. A larger current produces a stronger magnetic field. Thus, increasing the current flowing through the wire will enhance the magnetic field strength. Additionally, the closer you are to the wire, the greater the magnetic field strength. The field lines representing a stronger magnetic field are closer together, while those indicating a weaker field are more spread out. To determine the direction of the magnetic field around a current-carrying wire, we use the right-hand grip rule. This is a handy trick that can help visualize the orientation of the magnetic field. Here's how it works. Firstly, point your thumb in the direction of the current flow. Remember, conventional current flow is from positive to negative. Then curl your fingers around the wire. The direction in which your fingers curl represents the direction of the magnetic field around the wire. In diagrams or exam questions, the direction of current can be represented using dot or cross symbols. A cross indicates a current going into the plane of the paper, similar to the knock of an arrow moving away from you. A dot indicates a current coming out of the plane of the paper, like an arrowhead coming towards you. Using these symbols and the right-hand grip rule helps in correctly interpreting and drawing the direction of the magnetic field in various scenarios. In today's lesson, we delved into the magnetic field produced by a current-carrying wire. We demonstrated how an electric current flowing through a wire generates a magnetic field around it, which can be observed using a compass needle. We then examined the shape of this magnetic field, noting that it forms concentric circles around the wire and that its direction depends on the current's flow. To determine the magnetic field's direction, we introduced the right-hand grip rule, a practical method that uses the orientation of your fingers and thumb. This knowledge enhances our understanding of electromagnetism and the interrelation between electric currents and magnetic fields. Watch the rest of the GCSE physics course at Sophos Education.